So we have this XML file which consists of opening tags and closing tags that represent a hierarchical structure. So we could also see it like this, right? We have a tree representation of such a file. So we can see that the tags that are included, for instance here from the members on, they're all in this lab. So they basically all fall in the subtree of this lab that we have here. Okay. So XML, today we can find it really almost everywhere actually. It is used as standard file formats for Office, Open Office, these type of things. They are used for data exchange, but most importantly, where a lot of research is going in is for XML databases actually. So there are XML databases where the data itself is actually stored in XML format. So clients can query such an XML database. They send a query to an XML database server. And in fact, you can query nodes from a particular XML file. So there are query languages. I'm not at all an expert on that, but like XPath or XQuery, where you could, for instance, select particular nodes. Like here, we would select a lab that has to be below in the tree, below a university. And the lab should be such that in the subtree there is a member where there's a professor that has a specific name. So they're like relational databases. We can have similar queries. Right, so now what we want to do is streaming XML. So we in fact, we just want to run over this sequence of text that we see in an XML file. And hopefully we do just one pass over the XML stream, use small memory, and try to resolve some problem on this XML file. So a main motivation is, as I just mentioned, are these XML databases actually. For instance, there is a lot of research going in just making a pass over such a database and answering a query, for instance, or these type of problems. So this brings me, to the to what we actually have to do from an algorithmic perspective. So given such an XML file that we have here, let's have a simpler notation. We basically write for an opening tag that we have here a U, we have here a U bar in the very end, and which would be the respective closing tag. And now basically what we are seeing in such an XML stream is essentially, well, it's a depth first traversal of this tree, the corresponding tree. So we would run basically around this tree. Whenever we do a down step, we go down in the tree, we have an opening tag, and when we go up in the tree, we would have a closing tag. So this is basically the way we traverse a tree, is basically given by depth first traversal. Now, from an algorithmic perspective, what is quite beneficial, what we can exploit is that simply, well, it's a very simple fact, but we see every tag basically twice. Because we see every node basically twice, we see it in form of an opening tag and a closing tag. And this we will make use in the following. So the type of problems I want to consider are a very fundamental problem, which is the problem of well-formedness. So first of all, we want to know whether this one is well-formed because an opening tag X, Y will be closed in the right order, while this one wouldn't be well-formed because here we have Y and it would be closed by an X, which is not what we want essentially. So we want to figure out whether the underlying XML file has this property or not. And then once we know that an XML file is well-formed, we can ask more questions. For instance, we can ask whether the XML file fulfills certain structural properties. Like, for instance, we would clearly want that a lab in our XML file is included within a university, but we don't want that the university is itself included in a lab. So we would try to answer some structural properties about the XML file itself. And finally, these type of problems that I will describe, they are in fact quite related to a problem related to priority queues and a partitioning problem on XML files. So I just mentioned them in the very end. Okay, so this is based on this work of Magnès, Mathieu, and Nayak, well-formedness. So fundamental to this checking well-formedness are Dyke languages. Dyke languages are essentially the language of well-parenthesized expressions. So here we have two examples. So the first one is clearly well-formed because these brackets are first closed and then the parenthesis is closed, while this one is not well-formed. So the dike k would be well-formed, well-parenthesized expressions that have k type of parentheses. And then clearly an XML file is a dike language essentially, because we could just, if we have the sequence of opening and closing tags, we could replace them by parentheses, and that simply is a dike language. So it basically boils down to checking whether an XML file, whether a dike word is essentially well formed. So the first observation, the important observation, is that in fact it is enough if we were able to check whether an XML file is well formed that has two different type of tags, two different type of parentheses, because there's just an encoding trick that we could do. We take here we have many different parentheses, but we just, using two parentheses, we encode basically the index of the type of parentheses. So we could just take the parentheses of type 1, we replace it by two simple opening parentheses. The two we would encode by a parenthesis and a bracket, and we continue like this. It's basically like just taking the binary representation and using two type of parentheses encoding this binary word. So we can essentially just assume that our XML file has two different type of parentheses. So how can we check that? Well, let's look first at a very simple case. So suppose we have a sequence of opening tags and a sequence of closing tags. So in fact, we will define something like a height, which would simply be the number of opening tags that we've seen previously minus the number of closing tags. So if we have a sequence of opening tags, the height of these parentheses would just go up here. And then essentially just to validate whether, this particular instance is correct or not, essentially we have to solve a type of equality problem, right? We have to simply take the reverse of, for instance, this side and compare it whether the reverse of it is identical to what we have on that side. So this is very much related to the equality problem in a communication setting. And this can clearly be solved with just a polynomial hash function. So what we can do is we just take a prime that's sufficiently large. We compute a hash function of, say, the red parenthesis would be alpha to the height modulo p, where alpha is just chosen between 1 and p minus 1. So we have basically polynomials over this finite field here. The hash of the closing parenthesis would be just the minus of what we have here. So whenever we see the two, they cancel each other out, essentially, when we compute the hash of a whole word. So the hash of the whole word would simply be the sum over the hash of each element. And the interesting thing is we can do that and at the same time just ignore the other type of parenthesis. If we ignore the other type of parenthesis, we would still, when we see a closing tag or an opening tag, we still adapt the height of the respective, of all the other, so they still affect the height of all the other parentheses that we have. So, and you can essentially see that by just ignoring the hash values of the blue ones, we will still be fine. They automatically have to be correct then for this particular simple instance that we have here. So basically all we have to do is we maintain this linear hash value, and if the hash value is 0, we are well formed here on this instance. Otherwise, we are ill-formed with high probability. That's that's what we can get here. But now, of course, the instances that we look at, they don't have this particular form. So we want to see, for instance, if we look at this. This instance is well formed, and the hash, if we compute it as we did before, would be 0. But this one is ill-formed, because here we have a blue opening parenthesis and it's closed by a red one here. So, but still the hash value would also be 0, because it doesn't really affect here the order. So in fact, what you can see is if we have parentheses at the same level, if we only have at most 2 parentheses at the same level, like such a pair here, like the blue and the red one would be at the same level. In this instance, we would have 4. But if we had only 2, then we can be sure that in fact, if the hash value becomes 0, the instance would be well formed. So the key idea here is that, we just try to use many different hash values so that we can ensure that at each level we have at most 2 parentheses essentially. So how does that work? As an algorithm, we do the following. So we read blocks of size square root of n if the instance is of size n. We would simply first, we read this block, and we would do local, we would locally check whether here we have, a sequence of opening tags and a sequence of closing tags. We would just validate them and check whether this bit is correct. So we can locally already decide quite a bit. And we do that everywhere. So we have these blocks, and this basically becomes flat here because we already checked that these bits are correct here. Now, our goal was to use different hash values so that for each hash value we have at most 2 parentheses at a certain level. So what we would do is, let's take the first hash value. So we have a sequence of opening tags. This has been already checked. It goes still up. Then here we would go down. And we end up at this level, at this point here. So from here to here, we would use 1 hash value. But then we initiate a second hash value as soon as we go up again. So every time we have such an alternation, we go up, we go down, we start a new hash value. We go up, we go down, we start a new hash value. And you can see that, in fact, per block, since we have square root of n, size of square root of n, there is at most 1 new hash value that we have to initiate. So in every block locally, we have a sequence. We have at most 1, increasing and 1 decreasing sequence, which means that in total you would also need then square root of n hash values in total. So this algorithm gives, in fact, a 1-pass algorithm is randomized, of course, with approximately square root of n space. So clearly the question is, can we improve on that? And so there was a lot of work that went into that. So in the initial paper of Manias, they proved that in 1 pass you can't improve on that. So they have the right matching lower bound, in fact, for 1-pass algorithms. Now, what happens if we do multiple passes over the stream? And in fact, we can't really improve on that because we have lower bounds of the form square root of n over p for the number of passes. So if we do multiple passes in the same direction over the stream, there's not much we can do. However, if we use a pass in reverse direction, so if we get only a 2-pass algorithm where 1 pass goes from left to right and 1 pass goes from right to left, actually the memory goes down to log square, which is a quite curious phenomenon that you can, in fact, by a reverse pass reduce the space by quite a lot. But if you have passes in the same direction, you cannot improve by much. This phenomenon will also appear for the next problem I talk about, and I will go into more detail and show why this is actually the case for different problems. Okay. Are there any questions so far? Okay. So let's look at the problem of validity. So now we have an XML stream, and suppose the stream describes this tree that we see here. So there's a notion of DTD validity. DTD is a document type definition that looks as follows. So for each potential label that we have in the tree, like R, we have assigned a regular expression. Here we have B, we have a different regular expression here. And the goal is to check that the sequence of children that we have of a node, R has the sequence of children B, 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 C, that it matches actually the regular expression that comes with it. So we have given the set of regular expressions. We want to do a pass over the stream and validate whether for each node this is true, that the sequence of children fulfills this regular expression. So the difficulty is, if we look at it, we want to validate the node V. So where do we see actually the children tags in the stream? Well, at some point we see V bar is the closing tag, and then the tags are scattered all over the stream. They could be at any positions, essentially. So intuitively, this means that it's probably quite difficult to actually validate all the nodes in 1 pass. So here we see this. So in fact, you can see there's a lower bound. So if you want to solve this problem on this tree that we have here, so the DTD is designed so that the root node R allows as children only combinations of the forms. The leaves below are either 0, 1, 1, 0, or 0, 0, but they're not 1, 1. So this, in fact, if we have this particular instance, why is it difficult? Well, we do a depth first traversal, we see all these left children here, so this part of the stream. And then we see the blue ones. So this means essentially up to half of the stream we can't have validated anything so far. And in fact, this is just an encoding of the set disjointness problem for this XML validity problem. So in set disjointness, we have two players, and well, we heard it a couple of times already in this workshop. And this problem is known to be hard, that essentially in one pass, every algorithm requires linear amount of space, and even multiple passes don't help much, essentially. So the validity problem is clearly very hard to deal with. So, but what can we do? Can we do anything for this type of problem in the streaming setting? Well, it turns out that we can, in fact. And we can first, for instance, look at XML files that encode binary trees. So for a binary tree, well, we have to check that for all internal nodes P, we have to relate P somehow to the children, U and V. And suppose simply we have a check function, because we can simply check whether the regular expression matches this U and V that we have here. So it means when we traverse this tree, we have two chances to verify P. So either we will see P at some point in the stream, afterwards we see U, the opening tag, and at some point when we come up here and go to the other side, we see this U bar and V, the closing tag of U and V. So this would be one possibility, because we have all information. Basically in a top-down way. We used P and then kind of UV. But we could as well use simply UV, and when we return, we see P in the end again. So that has this particular structure that P appears twice in the stream as an opening and a closing tag, and we could basically have two chances in a way to validate this particular node. So in fact, yeah, that's what we meant. We either store P until UV arrives, or we throw P away when we see it and we store UV until P bar arrives. So using the simple observation, we get in fact also a square root of n algorithm, space algorithm. So well, we process, as before for the problem of well-formedness, we process the stream in blocks of size square root of n. Next, we simply look at all sequences where we have a U bar and a V, basically a closing tag and another opening tag in this block, and we try to validate it. If there's the parent node in the stream, great, we can validate it. If it is not, we simply store this information of UV in the block, and we will later on see the P bar, the closing tag of the parent node. So we basically defer this verification until this P bar will appear in the stream. So then the space complexity is simply the block size, which we have chosen square root of n, plus the number of deferred verifications, because we have to kind of accumulate them and verify as soon as the parent node comes. But then you can show, in fact, that in each block there will be at most one of these U bar V nodes that doesn't have a matching parent tag in this block. So we will accumulate, in fact, at most also square root of n elements that we have to validate later. So this is, in fact, it is very, very similar to the algorithm that we just saw for well-formedness. So one difference, for instance, is that this is purely deterministic, while it was a bit more complicated, this basic problem for well-formedness, where we needed a randomized way to deal with that. Okay, so binary trees give square root of n here in one pass. Now, we will try now to design an algorithm that does, in fact, two passes, one in normal direction and one in reverse direction, that gives a log square space algorithm, in fact. And here's the idea for these binary trees, for the special case of binary trees. We will simply ignore always this first opening tag that we see here. We will always do basically bottom-up verifications. We store this U bar V and wait until we see this P bar in the end. So what will happen is, well, let's take a stack. We go down here this tree, and every time here we see U1 bar, V1, we put it in the stack. Here we see U2 bar v2, put it in the stack, and we just accumulate all this information here in the stack. Well, if we do that, we would potentially need a very large stack here, because it could be that the tree is very, very deep, of course. But what we will do is, well, we just verify when we go up. So when we go here up, we kind of remove these elements from the stack. So this algorithm is good because it verifies all nodes, but of course the stack is large. So what we do is essentially we'll just remove some elements from the stack so that the stack won't grow too much, essentially. That will be the main idea. So we will reduce the stack to log n elements, and we do it as follows. Well, we remove all pairs u bar v so that the parent node has a smaller left subtree than a right subtree. So what it means is here in particular we have u1 bar v1, so we have this element on the stack. We have also this element of u2 and v2 in the stack. So right now we are at some position c. So how can we know that, for instance, this element q has a smaller left subtree than right subtree? Well, we can actually extract this information from what we see here. We know that the current position C, where we're currently in the stream, minus U2 bar, which is here, this is a lower bound on the size of the right subtree in a way, because, well, we basically can only see these elements that we have in here, and we see starting from U2, because the subtree here, V2, it starts immediately after U2. So we can kind of, by seeing where we are currently in the stream, we can infer a lower bound on the current subtree that we have. Similarly, we can actually infer an upper bound on the size of the left subtree that we have here, which we can get by U2, the position of U2 that we have in the stream, minus the position of U1 bar, because this essentially, U2 bar is the last item we see when we leave this subtree here. So then all these elements are seen between U2 bar and in fact here the U1 bar that we have here. So basically by only local information that we store anywhere in the stack, the positions, we can infer whether this property is true or not. And we will simply delete then an element from the stack if ever this condition is fulfilled, which gives us essentially this condition about the sizes of the subtrees. So, okay, so if we do that, we can see that in fact the size of the stack can't be larger than log n. So the reason is essentially, well, it's essentially we just have this deletion rule, and we will. This gives us in fact bounds on where in the positions in the stream of the elements where they appear. For instance, you can quite clearly see that the position of the U2 closing tag that we have here will be of the current position. Well, if more than half of what we've seen, we will have the U2 closing tag. For the next one, U3, simply by validating this position, we would be at least at 3/4 of where we are currently. And if you continue like that, you see that you only need log. You only have space basically for log n elements in the stream. So why is this now a good algorithm? Well, we were able to validate all nodes that have a larger right subtree than the left subtree. But now if we did a pass in reverse direction over our stream, well, left subtrees become right subtrees. They basically change the order. So basically in one pass we validate all with a large left subtree, and then in the reverse direction we just validate automatically all with a large right subtree. So this gives us a log square algorithm. So this is quite curious because it has this. The behavior is basically the same as for the problem of well-formedness. Validity of binary trees behaves in a way very, very similar. But now we still would like to do something, at least for general XML files concerning their validity. We had this strong lower bound that we have to at least solve set disjointness from communication complexity if we want to do anything. And well, set disjointness can be solved, but only if is not the right word, but if we use, for instance, multiple streams. If we look at a situation where we have an input stream, which will be our XML file, and then we have auxiliary streams onto which we can essentially write while we process the stream. And later on, we just read from the stream that we have temporarily written on. Then we can, in fact, we have additional power and we can solve, we can solve more problems. So here's an example. You can, for instance, implement merge sort with simply 3 additional streams, log n passes and log n space over the data. So for instance, we want to sort here the sequence x1 to xn. Well, what you do is you run over the stream and you alternately copy them on stream 2 and stream 3. You just basically alternate here. And then you just run over stream 2 and stream 3 and you merge them together in the right way that x1 and x2 will be, will be sorted. So we would get a block of x1, 2 that is sorted. And you just continue like that. So you basically copy them on the streams 2, 3, and then you merge them together in passes. And every time, essentially, simply the size of a block doubles. So you need only log n passes. So, right. So we will use some similar ideas like this for, in fact, solving the validity problem. And by the way, it's worth mentioning that this is essentially best possible for sorting. So there are lower bounds for multistream computation that show that, in fact, if the random access memory that you use in addition to these streams is only sublinear in n, slightly sublinear in n, then you do need, in fact, log n passes to sort a stream. Okay, so what we will do is the following. We will now use these additional streams that we have, and we will encode our XML document differently in what's called a first child next sibling encoding. This is basically an encoding of an arbitrary unranked tree as a binary tree. Then once we have a binary tree, we will look at the binary tree and see that it actually behaves very similar in terms of validity to the validity problem that we just studied for binary trees. So then we could, for instance, once we have the binary tree using 2 bidirectional passes and log square space, we can validate it. So how does this work? So the first child next sibling encoding looks as follows. Here's our original document. So you keep the edges to your first child and you remove all other ones. And then you simply connect the children among each other like that. So these children are, for instance, connected here. And this gives you the first child next sibling encoding, because essentially a child is, of, for instance, B is the first child that we had and the next sibling. So our goal is to compute this first child next sibling encoding, and we do it as follows. I mean, the number of nodes are identical in both encodings, and in fact, if you look at it, even the order of the opening tags in both encodings is the same. So here we see R, B, A, C, and this order will still be the same in terms of opening tags, R, B, A, C. And we continue like that. So in fact, computing this encoding only corresponds to changing the position of some closing tags in the stream. Because, so basically, what we do is we run, in a way, a kind of merge sort algorithm with these 3 additional streams that reorders the closing tags and, in fact, allows us to compute this first child next sibling sibling encoding. I don't go into details here, but yeah, let's assume we have this encoding. Well, now it has a very nice property here. So in the original tree, we want to relate, for instance, if we want to validate the node R, we need to know the information of B, 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 C. But now we see that in this tree of the first child next sibling encoding, the tags B, 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 C, they appear in fact next to each other. They appear here as a C bar, B bar, B bar, and B bar. So they appear in reverse direction as closing tags here in this encoding. So when we run our binary tree algorithm later, we will just simply, when we see the sequence of closing tags, basically compress them into one state, and we only have to relate then the state that we end up here to the parent node. So that is the key idea of this algorithm. Right. So if we do this, what we get, these are basically the results to summarize. For unranked trees, this gives a log n passes, 3 auxiliary streams, and log square space deterministic algorithm. Then we have this lower bound that p passes don't really help because of the set disjointness problem if we have only one stream. And we have particular algorithms for two-ranked trees that are essentially used here for also for the algorithm for unranked trees. Okay, so I want to mention now two other problems that are very much related. So one problem is the problem of priority queues, like validating whether the trace of a priority queue essentially is correct or not. And the other one is a partitioning problem of XML documents. So for the priority queue problem, what we have is the following. We see a sequence of, well, insertions. For instance, we insert into a data structure a 5, a 7, a 3. Then you call, for instance, an extract min, which should extract max, which should give us the largest element that has been inserted so far into this data structure. And suppose we see only the sequence of insertions and extractions, we would like to know afterwards whether, well, the sequence is correct or not. So for instance, we insert 2, 3. Well, when we extract something, it should be the 3 because that's the max that we've seen so far. This one would be incorrect because here we extract the 1, but the 1 is not the max because the 4 is also in the data structure. So the goal is to essentially check whether such a priority queue behaves correctly. And in fact, we have again the same phenomenon. We have a 1-pass algorithm with square root of n space, and we have a bidirectional 2-pass algorithm with log square n space for this type of problem. So this behaves again similar. And yeah, these are basically the 3 problems that are known, that I know where we can observe this phenomenon. So it would be very interesting if we could find others, in fact. Okay, last I just want to mention further XML algorithms, and this is a very recent work where in fact we want to take an XML file, do a pass over the XML file and partition the XML file into a couple of different parts. So here, for instance, we would like to partition it in 3 parts, and we would like to, well, partitioning means essentially we output where the separators in the stream are, that we get different kind of subtrees. The goal here is to balance the weight of the subtrees. So this would be a streaming approach to partitioning partitioning XML files. And in fact, these type of algorithms that we can get for this type of problems are in fact also very well sublinear space. So they are only linear in the number of partitions that we need, but otherwise we have essentially only a log n space and some dependency on epsilon here for these type of problems. So to summarize within this talk, yeah, I think essentially the question, what can be computed given just the trace of a depth-first traversal of a tree is much more interesting than just with applications to XML files. So I wonder what else could be done in this direction. Okay, and that's basically it. Thanks.